I will, let me get started here, guys. Well, we should get started. I will get my whistle. I will get the whistle. If I need to, I can go get it. I'll play that song again. No? My threats mean nothing to you? All right. Hey! There we go. Okay, that worked. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students and for the fellowship in this class and for a good break. Help us to glorify you what we do this day. Help us to just wrap up our thinking on this material, Lord. In your name I pray. Lord Jesus, amen. All right, so, oh yes, the top hat. I know you're all waiting. 2325. So today, we don't have too much to cover today, hopefully. So today I want to talk about non-Euclidean geometry, physics, some directions that math has gone, and of course also take any questions you might have about quiz 3, and hopefully look at the extra credit project a little bit. All right, so let me get straight into it. Everybody write down the top hat number so I can go on here. All right. So let's talk about the history of geometry briefly again. So it starts, I think, arguably with Euclid and his Elements, right? And so Euclid's Elements is, Euclid's ancient Greek mathematician, and I don't know, yes, Euclid put all these things together in a book which we still have copies of in some sense, not originals I don't think, but people talked about this for a couple thousand years, so there's a lot written about it. And but I think it's also fair to say that what Euclid wrote down was actually sort of a summary of the known things at his time, right? It's probably not the case that all of the things that Euclid wrote in his Elements were original works of Euclid. It is probably more of a summary of the things that were known at that time. Anyway, so there are these 5, the basic postulates in Euclid's Elements are to draw a straight line from any point to any point, to extend a line segment, to describe a circle at any center or radius, all right angles are equal, right? So these are the first 4 postulates of Euclid's Elements. They're all relatively easy to understand, right? I mean, they're not that weird. And then you get to the parallel postulate, which is if a straight line falls on 2 straight lines in such a manner that the inferior angles on the same side are together less than the 2 right angles, then the straight lines, if produced indefinitely, must on that side on which the angles are less than the 2 right angles. And you go, huh? So that is a fancy way of saying that if you have a line, right, and then you have another point off the line, then there's a unique parallel line that goes through that point, right, which is why it's called the parallel postulate. Although I think if you look at the original language of Euclid, you can see why people were kind of like, what? I mean, the first 4 are very succinct and nice, and then this fifth postulate, the parallel postulate as it's known, it just seemed wrong, right? It seemed unnecessarily complicated, and as such, there were a bunch of mathematicians who tried to derive that parallel postulate as a consequence of the others. So I told you some of this story last time, but I'm just going through it again here a bit, and I just wanted to write some names down for you. In particular, well, these names are hard for me. I can't even pronounce it, but IBN Al Haytham. So this is 11th century. You also had a fellow named Omar. I can say the first name. and then you got Khayyam. This is 12th century. You had another name here, Nasser al-Din. So in the Arabic world, there were mathematicians who worked on this and tried to derive the parallel postulate from these other postulates. So a bunch of people tried to do it over the centuries. And then, let's see here, slightly more recent, you had Lambert. I don't have a date for Lambert. And I don't, well, I'm probably mispronouncing this horribly, but I think I got the Giovanni okay. And maybe the Girolamo, probably. I'm starting to be a little bit suspicious of that. And I know I'm going to butcher the last name. Saccheri. This is 18th century, so that's the 1700s, right? And so all these people, they tried to prove that the parallel postulate was a derived consequence of the first four, all right? And so I think Lambert and Saccheri, which is, I'm sure, not the right way to pronounce that, they had, let me just mention this. I think these are kind of useful. So here's the Lambert quadrilateral. So Lambert, one of his ideas was you could kind of understand the issue of the parallel postulate by looking at a quadrilateral. And his quadrilateral, the way Lambert did it was this. He put 3 right angles in it. So you got 3 right angles. Right angle, right angle, right angle, right? And so here I'll read you a paragraph about it. A Lambert quadrilateral is a quadrilateral with 3 right angles. The 4th angle of the Lambert quadrilateral, I can't say words, oh my God, it's just getting worse. Quadrilateral, that's not right either. It's acute, pronouns to the rescue. It's acute if the geometry is hyperbolic, and it's a right angle if the geometry is Euclidean, and it's obtuse if the geometry is elliptic. So let's see here. This is this would be acute, right? Euclidean, we know and love that, right? So the rectangle has what? 4 right angles, right? That's Euclidean case. And then, let's see, what was the other? Obtuse. I'm trying to think of how to draw that. What's the other picture look like? I've got, I guess it's, I'm having a hard time drawing it, but I guess it's like, I don't even know how to draw it. Rats. Oh, and they don't have a picture of it either. No. Anyway, so I'll put a question mark over here. I'm not quite sure how to finish that picture. But this is the Lambert quadrilateral. And so in the Euclidean case, you can see that you'd have 4 right angles, right? But up here, this would be acute. This is in the case of hyperbolic geometry. So Lambert looked at these quadrilaterals as a means of understanding this parallel postulate in terms of looking at rectangles. You know, in the Euclidean case, in the parallel postulate, you could somehow get from this to the idea that the rectangle should have 4 right angles. Then Lambert, well, not Lambert. I just talked about Lambert. The other fellow there, Saccheri, let's say, he looked at what are called Saccheri quadrilaterals. And these things, here I can draw I think I got room in here. I can draw the three cases. So the hyperbolic one, oh man. So they could either look like this, They could look like, well, like this. Or they could look like that. So we have right, what's called obtuse, and acute. So in the Sakari quadrilateral, it's a quadrilateral with two sides of equal length, and both perpendicular to a side called the base. So the base, is, well, I've written as the base. So these are quote unquote right angles in the Sakari quadrilateral, and then the summit angles of the Sakari quadrilateral are acute if the geometry is hyperbolic, and the right angles are the right angles if the geometry is Euclidean, and they're obtuse angles if the geometry is elliptic. So this is, let me just write that on top of there. So I've talked about this. So Euclidean, that's what they look like if the geometry was, what did I just say? Hyperbolic over here, and over here elliptic. So now we talked about these different, how did we talk about the different kinds of geometry? Do you remember? So we had Euclidean geometry, and then on the other side of things we either had elliptic geometry or hyperbolic geometry. We talked about this in terms of triangles. Do you guys remember what the story was? What's the three different kinds of triangles you can look at? If I can squeeze that in here. Well, I guess I'll. So the three different triangles, of course, were like a triangle on a hyperboloid, like a chip, you might think of it, if you could imagine that. So this is the hyperbolic case. Of course, the Euclidean case is like that, right? And then I have trouble drawing it. Just a second here. Every so often, I just cannot think of the picture for the elliptic triangle. I mean, I can draw it on a sphere. I'm trying not to do that. Oh, okay, so just kind of like imagine blowing out the sides of the triangle like this. Something like that. So this is Euclidean in the middle. So you guys can tell me, what's the sum of the interior angles in the Euclidean case? So what was the story here? The sum of the angles. What's the difference between the hyperbolic versus the? So if you take these three angles, let's say alpha, beta, gamma, alpha, beta. I regret making this so small. All right, I'm going to bail. I'm bailing on this slide. See over. Sorry. Poor planning. I worked myself into a corner, literally. Let's see here. So 3. Make that much bigger here. So you've got something like this kind of triangle. You've got, of course, plain old Euclidean, and then you've got the triangle, what it could look like in the, so here we have hyperbolic, we have Euclidean, and we have elliptic. And I just want to talk to you again about the angles. So if the interior angles here are alpha, beta, and gamma, what can we say about the sum of alpha, beta, and gamma in each of these different cases? How does it work? So I'll do the easy part. Alpha plus beta plus gamma equal to what? 180, right? We know this. Maybe we learned this in middle school or something, right? Maybe, well, probably, hopefully elementary school, right? How about hyperbolic? What's the sum of the angles in a hyperbolic case? I'm not sure exactly, but it's going to be less than 180, right? And for the elliptic case, the sum of the angles is what? 180 degrees is less than it. So it's bigger than 180. And your book also mentions that it's less than what? If I remember correctly, I believe it's 540 that goes here. Now, if I have to correct that later, I will, but that's what my memory serves me correctly. And so if you think about that, anyway, there's that. So I'm trying to think the spherical triangle we looked at, it had 3 right angles, right? So it had 270 degrees. But anyway, so these are the 3 different kinds of geometry. And what was the modification of the parallel? How did the parallel postulate get modified in each one of these geometries? Do you guys remember? So we had what? If you give me a straight line, and over here, if I have a straight line, right? And I have 1 point off the straight line, what's the story? Straight line, a point off the straight line, what's the story in each case? So of course we know in the Euclidean case there is a unique parallel line, right? So it's just this, right? That's what we're used to. In the hyperbolic case, what's the parallel postulate get modified? It gets modified to say that there are more than one line that goes through that, right? So you might have you have like this is one, and then you might also run into things like this might be a straight line, and so forth. I won't try to draw it. I had the explicit. Remember the picture I had for you guys, the model of the Poincare plane. We had these. These are the straight lines, right? And so like, if I take this is a straight line and this is a point off the line, then well, anyway, let me not try to recreate all that here. Sorry. So we had more than one line parallel, a unique parallel line, and then what was the elliptic case? There is no parallel line, right? So the history here that I was mentioning, right? We had these guys back here, right? Up through Lambert and Saccheri. Now, Saccheri is interesting in that he proved a bunch of things. I wish I could find the name of his work. Find it here. Rats. So I mean, what happened with some of these fellows that I just put the name of there is they worked very hard to prove that you could do everything without the parallel postulate, right? And so what that ends up meaning is logically they proved theorems in the hyperbolic geometry, so if you can prove a theorem independent of the parallel postulate, it's a theorem of what's called absolute geometry. All right, flash forward here a bit. We get to the 19th century. In that we had Gauss and this one's hard for me. Lobachevsky, Lobachevsky, and Bolyai, Bolyai. So Lobachevsky was Russian. Bolyai was Hungarian, and Gauss was German. So all 3 of these people. So you could take a look back at Saccheri and these other people and say, well, they did things without the parallel postulate, right? So that was non-Euclidean geometry. But did they really understand it was non-Euclidean geometry? Arguably, no. It was these 3 people in the early 19th century. The timeline is somewhat debated, but something like 1832. Bolyai was, let's see here. Oh, excuse me, that was 1832. Misread it. Lobachevsky was like 1829 to 1830. Somewhere in there is where he published these ideas. And Gauss claimed to study it around 1820, 1815, somewhere in there. I'm not sure exactly. But so all three of these people, what they said is that there is a modification of Euclidean geometry where you replace the parallel postulate with a different postulate, and you can find logically consistent geometries. But really, their focus was all on the hyperbolic case, all right? Hyperbolic geometries. Then in 1854, you had Riemann. So Riemann, in 1854, he made a groundbreaking move forward. He suggested a way of creating new spaces in something that's called a manifold. What's a manifold? He coined the concept of a manifold. What is manifold? Have you guys read the King James Bible? Manifold's in there, isn't it? What does it mean? Manifold are your works. I think it literally means many folds, right? So like it's a concept of extension. But a manifold is roughly speaking, roughly speaking, our concept of space. Right? It's our concept of space. What is a manifold? So Riemann, he suggested there's this thing called a manifold, which is an extension of the concept of Euclidean space, much more so. And Riemann was the one who really pointed out that there's also elliptic geometry. But he did more than that. Okay, elliptic geometry was one of the things he gave examples. And he gave examples of, so I talked to you guys about a specific example of the hyperbolic geometry, that half plane with the circles and stuff, right? So Riemann didn't give just one example. He gave tens of thousands of examples of elliptic geometries, arguably. And how do you give examples of tens of thousands of things, right? Well, you don't do it by specifically writing down different axioms and stuff like that. He had formulas, all right? And so the way Riemann looked at space was through something called curvature. So he introduced curvature. And what's curvature? Now, when Riemann looked at curvature, he, I believe, only had curvature that was either 0 or positive, all right? And so you could have, let's call the curvature k for the sake of discussion. K equals 0 or k greater than 0. So if the curvature is 0, it's in what's called Euclidean space. Or you could call it flat space. If the curvature is positive, you're in an elliptical space. Right? Now, this is a very rough sketch of the history. The truth is that Gauss also looked at curvature. Gauss's theorem egregum, which basically means his awesome theorem, was a theorem which proved that the concept of curvature on a surface was intrinsic to the geometry of the surface and independent of how that surface is embedded in space, which is, well, I don't have time to really explain that, except to say that if you were a two-dimensional being somehow living on this surface, the curvature that your experiments which would reveal curvature of the surface would be the same no matter where that surface was where that surface was put, whether that surface lived in a 3-dimensional space or a 29-dimensional space, like that Gaussian curvature would be experienced in the same way. That's the idea of intrinsic geometry. Anyway, so now this is not Riemann. Riemann is another. So many of these names I'm naming, these people died at young ages because of fun 19th century things like tuberculosis or well, we talked about the duel before. There was that. I forget what got Riemann, but he didn't live that old. If he'd lived longer, there's no telling what this guy would have done. There's another fellow named Beltrami, which I'm sure I'm mispronouncing, and he talked about spaces of negative curvature. All right, this is about 1868, I think. All right. Okay, so all of this said, this all sets the stage. So about this same time, in terms of history of physics, what happened then? Do you guys know? In the 1860s, what happened? You're like, well, in America, it was kind of a dark time. But so in terms of physics, we just take a quick snapshot at the history of physics here. So about 1860 or so, Maxwell found his equations. So Maxwell's equations, what are Maxwell's equations? I mean, this isn't a course in physics, but let me just tell you briefly. I mean, I can write them down for you. You have the divergence of the electric field is the charge density divided by epsilon naught. The divergence of the magnetic field is 0. The curl of the electric field is minus partial B partial T. The curl of the magnetic field is mu naught times J plus epsilon naught partial E partial T. So I write this down mostly so I can just clarify what Maxwell did. Maxwell's really, really big contribution was adding this term right here. This is Maxwell's correction. To what's called Ampere's law. I say all of this to tell you that this discovery that Maxwell made laid the groundwork for radio. Because of that, Maxwell's corrections to Ampere's law, it was soon thereafter discovered that these equations permit solutions that are similar to waves, like waves on a string, which said that somehow electric and magnetic waves exist through space, like electric and magnetic fields can wave through space. And some 20 years later, I think Heinrich Hertz, right? Marconi, these other guys, they come up with radios and were able to actually show that these equations did have solutions and that, well, we have radio, we're still using radio, right? But here's the interesting thing about all this. Maxwell's equations had inside them this idea that the speed of light was just a consequence of the physical properties of space and time itself. So like implicit within Maxwell's equation, you have this idea that C is equal to a constant. I believe the formula is 1 over the square root of the permittivity times the permeability of free space. That works out to like 3.0 times 10 to the 8th meters per second, something like that. Just as a consequence of space and time itself, right? But this stands in like just bold opposition to Newtonian mechanics. Do you guys know Newtonian mechanics? Maybe you had a course in physics in high school, I don't know. So who discovered Newtonian mechanics? Newton, right? No, you're like, Bob, no. Newton discovered Newtonian mechanics. And that was what? That was about 1660, something like that, right? And then, of course, Newtonian mechanics was refined and improved over the next 200 years to it really reached a state of the art in the late 19th century. In the late 19th century, you could derive the motion of all the planets and moons and things like that that were observed in the known universe using Newtonian mechanics, except for a couple things. So it was incredibly successful in explaining the universe that was observed, right? Explained most planetary motion. except a couple things, right? There were just two sort of things that couldn't quite be pinned down. The one was the perihelion of Mercury, and the other, shnikes. What was the name of that thing? Well, the perihelion of Mercury. We'll just stick with that since I remember that one off the top of my head. But except a couple finer details, like perihelion of Mercury. And there were mathematicians who, this is before computers, right? So to do these calculations required incredibly sophisticated hand-to-hand combat with like detailed calculus. And but it was also very successful. But here's the thing. Newton's mechanics would say something like, if you had a wave, the speed of the wave should depend on its source. All right? So like, well, in short, Newton's mechanics was inconsistent with the Maxwell's equations. Like Maxwell's equations say the speed of light is constant. Newtonian mechanics does not allow for this. So what was the solution? So one of them or the other is wrong, all right? So like Newtonian mechanics says speed of light cannot be constant, right? Basically that's a... So what gives? Who won? Did Maxwell's equations win, or did Newton's equations win? I mean, Newtonian mechanics is mostly right, right? We still teach it in courses today because it's still mostly right, right? So what happened, it turns out Maxwell's right. And the modification of Newtonian mechanics which makes Maxwell's equations sensible is what's called special relativity. So special relativity who discovered special relativity? I can't spell. Sadness. I shouldn't try to spell and talk at the same time. Special relativity, this was 1905. And who did this? It was Einstein, right? So Albert Einstein came up with special relativity, which was a modification of Newtonian mechanics in which the speed of light is constant and the Maxwell's equations are naturally what's called covariant with special relativity. This is, but it came at a great cost conceptually because like special relativity says really weird things. Like the time experienced by different observers is different. So one frame of reference might say two events have like 10 minutes between them. Another frame of reference might say that those same two events have 5 minutes between them, right? That's really weird, right? Show of hands, who's seen Interstellar? Right, so that movie gives you kind of a window into this sort of thinking, right? That different frames of reference experience time differently. But anyway, let me get to the point here. This special relativity then led Einstein to take a deeper look at gravity. See, because gravity was solved by Newton back in the 17th century, excuse me, back in the 1600s. And the modification of general relativity, it turns out, right, so that's about 1916, 1920-ish, depending on how you want to dice it. Again, Einstein. And here's the interesting thing. Einstein's general relativity, what made general relativity possible to understand was exactly that mathematical system, that framework that Riemann had introduced some 50 years or so prior. So the mathematics that Einstein needed to write down general relativity were not really known to humans before about 1860 or so, and even then really just a very select cadre of mathematicians. And then the work that Beltrami and others like Levi-Civita and other people they developed something called tensor calculus, which then, when Einstein asked the right physical questions, all of a sudden he found out, oh, the mathematics to do general relativity is already there. And so what did Einstein's general relativity say? It said that this curvature that Riemann was talking about actually is how we understand where gravity comes from. So like the Einstein general relativity basically says that gravity is a consequence of curvature of space-time. So I think it's very interesting to study the history here, because you see that I can't spell. Consequence maybe. My spelling is degenerating. I need the winter break to come. Gravity is consequence of curvature. Right. So anyway, I just wanted to give you just kind of a quick snapshot of the history of geometry. And so geometry, non-Euclidean geometry, all led up to this. You know, what happened in the 19th century, the idea that Euclidean geometry wasn't absolute, then looking at hyperbolic geometry, which opened up the, world of possibilities, and then, Riemann's idea of space being more abstract. All of these things laid the groundwork for Einstein being able to think past our previous way of thinking to see this thing called general relativity, which, as far as I know, is still our pretty much best theory of gravity. General relativity has some experimental verification at this point. I think about 10 years ago or so, we discovered what are called gravity waves. So if you have something really, so mostly speaking, you don't feel the gravity of the Earth change, right? It's just kind of what it is, right? But if you had really, really severe, like huge galactic events, you could create waves in gravity and experience those. So like something like, I don't know, like a neutron star collapsing into a black hole, something really, really massive. They set, how they detect gravity waves? Basically, they set up giant triangles. At least this is one of the experiments that they were going to do. I think the actual way they did it was more complicated than this, but one of the experiments which was being proposed, some time ago, was basically to set up a giant triangle in the space. So you have like 3 satellites really, really far apart with lasers connecting them, and then you can measure the angle in the triangle, basically, and you can detect the angle departing from 180 degrees, and in so doing, you can detect the curvature, because if the angle isn't summing to 180 degrees, well, then that shows you that, the space is curved. And in fact, Gauss was actually trying to measure this back in the 19th century with surveying work. Of course, he didn't find it because space is really, really close to being flat in the bulk, if it's not flat exactly. But hey, whether or not space, like in the bulk, like the large scale structure of space and time, is it flat? Is it curved? Is the geometry of space-time hyperbolic? Is it Euclidean? Is it elliptic? This is an open question as far as I know, and it ties into this other thing that astronomers and so forth are looking at more recently, called dark matter and dark energy. The bottom line is we don't really know. If you listen to the experts, we don't really know what the large scale structure of space and time is. There are large unanswered questions in cosmology right now. Okay, enough about that. I promised I'd let you guys look at, I wanted to show you another way that math is used for physics. So let me go through that real quick. If you allow me this brief couple minutes of show and tell, then I'll get to your extra credit project here. Come on. Oh man. So you guys ever heard of quarks? No? Quarks. Oops. Nope. So, oh man, let me get this out of here. There we go. So I'll try to be brief here because I know we're a little short on time here, but This is a talk I gave back in grad school, actually. And I'm not going to show you all the mathematical details. I really just want to just tell you the story real briefly. And the story is this. So in the 1920s or so, we did experiments colliding these exotic particles called pi mesons into neutrons and protons. And we observed all these different interactions. And people looked at it and they tilted their head and squinted and they realized that there's something called isospin, which was conserved in these interactions. All right? And as the time went on, the number of known particles, it kept increasing until you had what's called the particle zoo. And so the particle zoo, here it is, included things like these kaons, these pions, I don't even know the name, whatever that is, right? Sigma plus, sigma minus. So you can think of these particles as sort of excited states of neutrons and protons in some sense, right? So you had all this mess of particles, which you could make these diagrams, analyzing them in terms of their hypercharge and isospin. And they made these nice pretty patterns, right? And the interesting thing was that in the late 50s to early 60s, they noticed that there was this pattern, these delta particles, the sigma particles, these guys I don't know the name of, and then this was not found. So you had all this pattern, right? And there's just something missing, right? So what do you say if you're a physicist and you see this pattern and you go, well, there's a triangle, right? So there must be something down here. And so Gell-Mann predicted in 1961 that there would be this particle called the omega minus. And it was very, very satisfying. I mean, not many people ever experience this kind of thing as a scientist. Make a prediction in 1961 that you should find a particle with these properties. And then in 1964, they find the omega minus particle, right? So this is a really brief synopsis of nuclear physics over the basically period of 1920 to 1960. So then the question is, why are there these triangles? Why are the particles making this triangular pattern? It's just something they've observed. Why, right? And this was the problem that was solved by Gell-Mann in the next few years, and others, not just him. But, excuse me. So it turns out you can build those pictures using more fundamental things called quarks, and the quarks have these representations in terms of the hypercharge and the isospin business, and new things called baryon number and strangeness. And I'll just get you straight to the picture. So like you can take two quarks, all right, you take two quarks and you put them together. The mathematics of that is a tensor product, and it's just these pictures can kind of show you. And so looking at two quarks, it reproduced that so-called meson nonnet. And also, perhaps more striking, is excuse me, you can take three quarks and put them together. When you take the tensor product of three quarks, then you generate all of these different possibilities that had been observed in nature. So this is the reason people think there are quarks, because if you take tensor products of the quark states, you could reproduce all of this data that we saw in the early 20th century. And so that was striking. This happened in the 60s, early 70s, something like that. But you might ask a simple question, right? So what's a quark, and have we ever observed one? Well, the answer is we haven't. So why do we believe there is such a thing as a quark? Well, it's basically these pictures, because if you believe there's such a thing as a quark, then you can generate all of the particles which we have observed and their interactions. So it's a funny thing, the way physics is right now. We have basic things in physics which we can't observe, and yet they have a lot of explanatory power. Anyway, I thought I should show you that. Sorry if it was not of interest. Now let me open up the floor for questions. You guys have any questions about quiz 3 or anything? Feel free to ask. I feel like there was something else I was supposed to talk to you about. I think I was supposed to talk to you about mathematical systems. I I will not ask a question about mathematical systems on test 3. There you go. So I think I currently have a question there on mathematical systems. I will remove it. To be fair, I haven't talked about that much. So, hey, what? Well, there we go. Well, you can do it. So how many people know about this? All right. How many people have not read their Canvas announcements? So it's okay. I don't read mine either. I don't really have any, except the ones I write. But this is the extra credit project, which I have made for you to get extra credit if you want. And I also think that this would be, now this will not help you with test 3. Is there a test 3? No. Quiz, yeah, there's quiz 3 and there's the final. And so how does that work? So the quiz, come on. Really? That's just aggravating. All right, so listen. Seriously? I will not miss using this thing. So to recap, quiz 3, this is not on quiz 3, all right? So this will help you with the final though, right? Because the final is comprehensive. I'm going to focus. The final is comprehensive, and it covers what? Test 1, test 2, and quiz 3, right? So we didn't quite have time for a test 3, and so I said, well, I do want to give you something in class with time pressure so that you have some estimate of what you understand about the part 3 material. Yeah. So we're doing that when? Thursday, right? So Thursday's quiz 3. That'll be the whole class. And then what happens? We have one class after that, which is what? Tuesday. And that will just be questions you have about all the material, right? I don't really have anything formal planned for that day except that we can open up the solutions for quiz 1 and test 1, test 2, quiz 1, quiz 2, quiz 3, and talk about how you solve things if you want, right? So, but I wanted to show you what I intended here for the extra credit. So when was this due? If you want to do it, you don't have to do it. And some of you got like 100% on both of the tests. I don't think you really need to do this if you don't want to. But you're the people who do it, if I had to guess. Anyway. My goodness. Really? Like, why? There. Oh, what? I may smash this. On the last day of class, I think I'm just going to bring this up here and just smash it into 1,000 pieces. I'll bring my sledgehammer from home. Just a second. I need to get a pen. I think my markers are going to be too fat to write in there. So you guys help me out. I'll do a couple of these with you, just so you know. Like, what would this one be? That's the what? That's the complement A union B, but what? What's our notation for complement? We use prime, right? So that is the complement. Come on. Ay, ay, ay. The complement of A and A union B. Does that make sense? If it doesn't make sense to you, you are exactly the person who should be doing all of these so that you don't get this problem wrong on the final, right? This is pretty much every conceivable case I can ask you. I think. I don't think I've missed anything. I mean, hey, let's do another one. How about this one down here? What would this be? No, let me do this one. What's this one? It's B, right? What's shaded in here? B. So what's this? Nothing shaded in. What's that? That's the empty set, right? Empty set. How about this one? It's not just A though, right?
Oh, B prime?
And it's not quite B prime either, is it? But we could, how about that? One way we could look at that is we could say B prime, right? That gets you most everything, right? Except what else is in there beyond B prime? What's this here? This is A intersect B, right? That's A intersect B. So if you look at this, this is B prime union with parentheses A intersect B, right? That's what's there. Does that make sense? So everything outside of B is B prime, and then you're also unioning with the intersection of A and B. So that would be that. Yeah? Want to do any more? Yeah. Let's see here. So you guys pick one more. The one underneath this one? This one? Oh, aw, man. All right, so this one here, let's see here. Oh, that's just B prime. That's everything outside B, right? Okay, fine, I'll do one more. The bottom middle one? That's a good choice. What's that? That's A union B prime, right? Union what? See, so look at this shape. It's everything that we had. Gah! Seriously. Everything we had up there together with the intersection, right? So it's the union of A union B prime, union with what? The intersection, yeah? All right. You got to do some of this, so I'm going to go on to the next one here. So I also, oh yeah, that's not it. Come on, what do you think? So let's do some of these. So I didn't want to put the letters on all the diagrams, so you have to refer back to the top to see the letters, yeah? So like here, let me do the easy one. This guy is what? A intersect B intersect C, right? Very good. What's the next one? It's A. Is it though? I mean, that's... So it's... What's this here? So we can say... We could do this. We could say it's A, and then we can use set difference, right? You remember what like A minus X? How's that defined? That's A in A, such that A is not an element of X. So this is called set difference. So basically, you want to take A, right, and you want to remove this piece down here. So you could remove. Let's see here, A intersect B, and A intersect C. I mean, there's other ways of doing it, but that's the way I'm thinking about it right now. So what I'm trying to say here is A intersect B. Let me go and flip ahead here. Like so I'm trying to find I may not have covered every single possible case here. Let me just zoom in there. Does this make sense? Let me use some color coding just so you see what I'm doing. So A intersect B, where is that? This is A intersect B, right? That's A intersect B. Where is A intersect C? Because this is A and B. Oh, come on. Up. That's A intersect. All right, that red part, right? A intersects C is this part. So you see, if I take those two together, that's the part that I need to remove from A in order to get the shaded set. So I take A and I remove those two pieces to get the shaded part. Does that make sense? Yeah. It's extra credit. I don't know. How many do you think it should be worth?
However much the final is worth.
However much the final's worth? That seems like a bit much. Let's say
About like 200 points. 250 points.
I'd be greedy to just say 150.
I think it's more fun to leave it undefined. No? No?
I'll give you a really good course evaluation.
You give me a I already gave you chocolate. And I brought donuts. Wait a minute, what am I saying? That had nothing to do with course evaluations. I think a point for each picture is probably reasonable. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. 42. Well, that's just meant to be. So apparently 42 points is what this is worth. Which is half a letter grade. Yeah? Almost. I mean, that'll take you from a high C to a low B, right? So that's something. When does this due? When? Did I say? Ah, where is this? Hey guys, please stop talking. Thank you. Ahem. 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 So somebody asked, where is this? If you look in announcements, yeah. And the extra credit, the last announcement I made here, Quiz 3 and the extra credit project, at the bottom of that announcement right there, see that? Venn diagram extra credit project right there. Click on that. There it be.
Print it?
Yeah, you need to print it. Why are so? Students are like. This is like a phase change just happened for me. Like I remember before I left Liberty a couple of years ago, I had students like print things out. It wasn't like people were not confused by this. Like all of a sudden after COVID, everyone's just like, it's on paper? Are you sure? It's on paper? What? No way. Like, yes, it's on paper. Please. You must physically turn it into me. Okay, so when was it due? The 6th. When is that? The future. So that's the last day of class. It is due the last day of class. I intentionally did this. Why did I make this due on the 6th rather than on like next class? There's a simple reason for this. This extra credit project does not help you with quiz 3. So I wanted to let you work on the extra credit project like after the next quiz if you want to. Yep. Now you had a question about quiz 3. What was on quiz 3? Sorry, I'm having trouble focusing for some reason.